So now, why does induction work? We didn't really cover that. We stated the principle of mathematical induction, but we didn't actually prove why it works. And so let's do that now. So recall from that previous video what the statement of induction is. So mathematical induction says, for all n, let P of n be a statement. As I said previously, this is just a technical requirement to make sure that P of n really is either true or false. No weird stuff is happening. Then provided the base case is true and the inductive step is true, then our statement is true for all n. Now, I won't give a completely rigorous proof here, but I will give a sketch of a proof. So let's assume the conditions of the principle of mathematical induction hold. Namely, I'm going to assume that both of these hold. So I'm going to assume that P of 1 is true and that P of k implies P of k plus 1 is true. And this second one, of course, has to be true for all k in n. Okay. Now, I'm going to define two sets. I'm going to define the good set, which will be G, which is n so that P of n is true. And we know, for example, because P of 1 is true, we know that 1 is in G. And then the bad set is going to be all the values of n that make P of n false. And as is typically interesting, the good set isn't so exciting here, and the bad set is the one where all the interesting things happen. And so the bad set, we can do a proof by cases, is either empty or not. Okay, so it's either the empty set, in which case I'm showing that P of n is true for all n, that would be good, that's what I want, or it's not empty. And if it's not empty, that's bad, hence bad set. So let's see why it can't be non-empty. Okay. So let's assume that it isn't empty. And let Q be the smallest element in this set. Okay, so this is just some set of natural numbers. Let's pick out the smallest one. If it's not empty, then there will be a smallest one. And that's the first sneaky thing that happens in this proof sketch, and we'll come back to that point at the moment. The fact that we can find the first number in that set. Okay, so it's not immediately obvious that we can do that. But let's assume B isn't empty, and let's pick out the first value of Q from this set B. And so Q is the first number that makes P false. So it's the first thing that makes our statement wrong. Well, because that's the first thing in the set that first thing in B, it's the first time P of n is wrong, well then we must have that the previous value of n makes it true. Okay? And we know that Q has to be at least 2, because 1's in there. So Q minus 1 has to be at least 1. So if P of Q minus 1 is true, well then we can use the inductive step. By assumption, P of Q minus 1 implies P of Q. This implication is true, this is true, so P of Q must be true. Except that Q is in B, so P of Q is false. So there's a problem. Q can't be in B, because P of Q can't be true and false at the same time. So the only way this can work is if no such Q. So there can't be any such Q. Well, if there's no such Q, if there's no smallest element in B, the only way that can work is if B is actually empty. So if B is empty, there's no n that makes P of n false, and so P of n is true for all n. And there's our sketch of this proof. And there's two sneaky things going on in this proof. The first is, it's really a proof by contradiction in disguise. And we haven't done proof by contradiction yet in this course, but we will later on, and we'll cover that a bit more carefully. The other thing that we're doing here is we're making use of what's called the well-ordering principle of the natural numbers. A set is well ordered if non-empty subsets of that always have a smallest element. So if we take a set of natural numbers that isn't empty, we can always find a smallest one. And this seems completely obvious about the natural numbers, but we should remember that other sets are definitely not well ordered. So for example, Z is not well ordered because I can take the even numbers out of Z, so all even numbers, positive or negative, and there's never a smallest element. I can always make something smaller. Similarly, the rationals and the reals are not well ordered. Okay, so we're really using something very special about the natural numbers here, that every non-empty subset has a smallest element. Okay, to stop there.